Thank you. Thank you for the nice introduction. Actually, I was a ASP postdoc at HAO 10 years ago. Time flies. Yeah, it's amazing. It's always so exciting for me to come back to HAO, especially during summer. But promise, it's not just because of weather. And today, I'm going to talk about the significance of Meso-scale structure to the ionosphere and the thermosphere. Before talking about science, I would let people know a little bit where I come from, University of Texas, Arlington. Whenever I tell people I'm working at University of Texas, Arlington, and the next question will be, oh, what is Arlington? Yeah, good question. What is Arlington? Actually, today, on the lunch table, I got the same question from my friend. Here's Arlington. Arlington is just sitting between Dallas and Fort Worth. And somebody say Arlington is in the heart of the North Texas area. That sentence must be from Texan, I think. Yeah. The airport is I think is here. We call it the DFW airport. So it's very convenient. We're right in the center of a big metropolitan area. It's convenient in many ways, in terms of shopping, or you want to find a good place to have dinner, or travel even. Because the DFW airport is the headquarters of American Airlines. So we pretty much have non-stop flight to most of city inside the US and to some city outside of US, like Beijing, Shanghai, Hong Kong, so which is very nice. And if Binzhen want to invite me to Hong Kong, it's very convenient for me. All right. Also, somebody say Arlington is a backyard of the DFW metropolitan area because it has relatively near two big stadiums. One is AT&T Cowboys football stadium, and another is a Rangers stadium, the baseball.
Do you have a Thornton Bureau grant?
We'll try. Next time. Both of them just finished in 2000, maybe 5 or 6 years ago. So it's fantastic. If you really enjoy watching games, that would be a good place for you to have fun, probably. If you're a fan of Cowboys and the Rangers, by the way. And then UT Arlington. UT Arlington is people say is a growing university, and just this year it has been rated as a Carnegie Research 1 university, which means highest level of research according to their category. And in terms of size, in 80 years, because I joined UTA in 2009, which is 80 years ago, and the student, we had 37,000 students. Now we have 57. So you can see the speed of the growing. And somebody says, wow, the rate is close to the rate of the house price in Beijing. I'm not exactly sure. I didn't do the comparison, but could be, yeah. And we offer a 180-degree in a quite in a quite broad range of disciplines. And now we go down. The scale size is getting smaller and smaller. Okay, then getting close to my topic, Meso-scale structure. Okay, and then we go to physics department. In terms of research expenditures, physics department is number 1 in the College of Science, so we're doing very well. If well, we're not afraid to compare most of the department in college engineering either. Even college engineering is so dominant in the university. That's probably, I don't know, it's a typical case in other university, but at least at UTA, that's the case. And we have 23 professors, faculty 23. While physics typically is large, if you go to UT Austin physics department, they probably tell you, we have more than 100 faculty, which division you want to. They don't know each other very well, even they are working in the same department. That could happen. But we only have 23, relatively small in physics, but we cover quite a broad range of areas. We have the traditional high-energy physics, condensed matter physics, and astrophysics. This is kind of a traditional area in physics. Also, we have relatively new fields, such as nanobio and, well, very importantly, space physics. And in space physics, currently we have two faculty, myself and Dr. Lopez. Probably somebody familiar, is familiar with Dr. Lopez. He had very close collaboration relationship with magnetosphere team at HAO, and he visited HAO last year, I guess. His research interest is about solar wind magnetosphere interaction, and my research is mainly about ionosphere thermosphere coupling and influence of different forces like solar irradiation, solar wind magnetosphere, and waves from the no atmosphere. Since I'm going down, I gradually approaching the topic I'm interested, and give a very brief introduction of the ionosphere. I don't know, most people really read that, but doesn't hurt to spend a couple of minutes. Well, first of all, I would acknowledge Stan. Thank you to sending me this slide 10 years ago when I was a postdoc here. I'm still using it, which is a fantastic slide.
I didn't make that slide.
Oh, didn't make? Oh.
I just have possession of it.
Oh, really?
It came out of the Time program.
Oh, Time.
PR slide for the Time program.
That's probably true. Time. Oh, I
see.
see.
URs, the Time.
That makes sense. Yeah, but I got a copy from you, so I directly give to my colleagues. Sorry, didn't trace back. And I found this slide is very friendly because upper atmosphere actually is the overlapping region between ionosphere and the thermosphere. Ionosphere represents the ionized species, and the thermosphere represents the neutral species. According to the neutral temperature, the atmosphere can be divided into 4 layers. The troposphere, stratosphere, mesosphere, and the thermosphere. So about 100 kilometer, due to the absorption of the solar UV, the temperature got enhanced dramatically. And this shows the temperature day and the light. The average temperature is close to 1,000 K, much higher than the rest of the 3 regions. That's why it's called thermosphere. Meanwhile, due to the ionization, solar UV ionization, there are abundant plasma in this region as well. And it has D, E, F1, F2 peaks, and we call it ionosphere. So ionosphere, thermosphere basically represent, neutral and ion in a similar altitudinal range. And these two coupled into each other in many ways. Here, this figure, hopefully I called it to the right person. If not, correct me. This is right. Okay, thank you. This figure is quite busy. It's a busy figure. But it gives us some impression how complicated the system is. The white arrow shows the ion, and the yellow arrows represent the neutral. So the neutral ions are coupled into each other through the continuity equation, through the momentum equation, and through the energy equation, all the way. And the major energy source for the upper atmosphere includes the solar irradiation, which contributes 80%, well, 70% to 80% according to Dolores' paper, averagely. And another energy source is electrodynamics and particle precipitation from the magnetosphere. And on average, it contributes 15 to 20%. But this part of energy varies a lot, substantially, especially during a storm event. It can be even larger than the solar irradiation energy input during a specific superstorm. Additionally, the tides and the gravity waves from no atmosphere can cause perturbation in the upper atmosphere through propagating upward. So pretty much done, I think. Now, but this movie I have shown many times, but I always like to show that because it gives us general idea how the space environment is connected to each other. Here is a movie based on the simulation conducted at the University of Michigan. So the center represents the location of the sun, and so the white line shows the magnetic field, and the plasma density is indicated by the contour, the color of the contour. When the CME ejected out from the sun, it propagating out into the interplanetary space, and not perturbation happens. Then the black line shows the simulation grid. Certainly is not uniform. And then we keep zooming in and in. Eventually, we get where we are, the geospace environment. And certainly, when the CME happens, the large perturbation also happens in our inside our geospace, including both magnetosphere and also upper atmosphere as well. All right. Some say, okay, sounds interesting, but why should we care? Why should we care about upper atmosphere and the space environment? Because our technology is based on the electromagnetism. That's why we always keep saying, space weather. I think there's a senator just passed the bill in May to emphasize the space weather and the space weather-related research. And, but anyway, now I'm going to mention a couple of atoms. Well, what's the consequence of, what's the influence of space weather to us? One is a satellite. Because the satellite, probably go back to this slides. The low Earth orbit satellites, like space station, are flying in the upper atmosphere. So the atmosphere drag is very important. It can change the satellite trajectory if the prediction of the thermosphere is different from the reality. And actually, that's what happened when we call the satellite has a tracking problem, which means the predicted position using the background model to predict the position of the satellite is different from the actual position because the atmosphere drag may be bigger than the prediction as well, maybe different, at least different from the prediction. And here, I think I borrowed Stan's slide again. Is that right?
Well, again, not a slide, but I know. I'm like a collector.
All right.
Archivist.
Well, I really like this slide. Okay. So you're one of them. Okay. The blue line shows the AP index. So up here indicates a storm happened. After the storm, more than 1,000 satellites had tracking problem. But of course, we get most of them back by retuning, and we're not going to really lose 1,000 satellites, but need extra effort. And when we have an inaccurate satellite trajectory prediction, something really bad can happen, like the collision of satellites in 2009. Two commercial satellites got collided into each other, which is so unfortunate. And in addition, it left lots of debris on the in the upper atmosphere, which can possibly damage the satellites having similar trajectory or having similar altitudes. And it can also cause interruption of the communication, for example, GPS communication and very high frequency wave communication, which has been used in military quite often. If you have a small scale structure of electron density, the refraction trajectory may be different from what to expect. And okay, so now we go to science. What's the scientific problem are important to us or to the field? Well, I think different people probably have different lists. In my point of view, first is the energy. How much total energy is deposited into the system, and what is the energy distribution? And secondly, some mechanism related with the meso-scale and the small-scale structures. The largest scale feature probably we understand quite well, but if we go to a smaller scale, there's still a lot of work to do in terms of mechanism even. All right.
Can you differentiate for us how you define meso and small here?
That's a very good question. Depends on who you're talking to. I asked the question in a workshop because everybody talking about mesoscale is so important, but actually the satellite observation and the ground-based observation and the modeler, they are talking about something different. So for our modeler, for our purpose, we defined 50K to 500K as mesoscale. That's a range, spatial scale range we're going to target. Here I list a couple of ongoing projects related with the mesoscale structures and energy input. And certainly I cannot talk all of them. I just briefly mention a couple of them. First is electric field variability and the impact on the energy inputs. And this work was done through collaboration with Astrid and ART when I was a postdoc here. And we're going to revisit this problem and make some improvement. That's why my grad student, Qin Yu, is visiting HAO, and we hopefully can make improvement, can build up a new component of the model. First of all, the motivation. Motivation is, if you look at the geoheating is proportional to the average of the E square. E is electric field square. And the average E square is equal to the E average square plus the standard deviation of E field, which indicates the average field and the electric field variability should play a similar role to the total energy input or total geoheating. And here at Mike Kontrowski use the radar observation shows the delta VI and the average VI actually is pretty much comparable if you look at the magnitude in statistical. And so people, basically this brings people's attention to the significance of electric field variability. And if you don't quite understand what I'm talking about, you can think about the DC current and AC current. So in terms of heating, they should be similar. Like AC current, even the average E is equal 0, but the heating effect definitely is not equal 0 when you're oscillating, okay, because it's proportional to E squared. Okay, can move on. And then, based on the D2 satellite observation, Astrid and Art built up a new empirical model for the electric field variability. So electric field is a vector, so it has two components. This is ED2 and ED1. Here it shows the dependencies of these two components on the MF angle. Certainly it's changed with MF condition significantly. Then we coupled the empirical model with TIGCM, see what the consequence will be in the thermosphere ionosphere. And the blue bar shows the integrated geoheating in the northern hemisphere when we only use the DC or average electric field or DC current, you can think about. We only use the average electric field, so the blue bar. And the yellow bar shows the Poynting flux, total Poynting flux in the northern hemisphere. And I think everybody took the E&M, right? Griffiths or Jackson. But if you're familiar with the Poynting theory, the total Poynting flux should be equal to the energy dissipated inside the boundary. Okay? If you apply the Poynting theory to the upper atmosphere, so the Poynting flux should be roughly equal to the total geoheating dissipated into the upper atmosphere. And certainly the blue bar is not close, even close to the yellow bar yet. But if we add in the electric field reliability, then we got the red bar. The red bar, in general, the total energy, in terms of total energy, is much, much closer to the total Poynting flux, which means by adding in the electric field reliability makes the total Joule heating more consistent with the total Poynting flux, total energy input. Go ahead.
So there are also two other terms in pointing here, is that the reactive power. So if you're saying this is carried by AC fields or currents, is it possible some of them are reactive power?
Again, I'm sorry.
So it's like waves oscillating in that.
Right.
It's like wave reactive power, dissipated power plus reactive power.
I'm not exactly sure about you're talking about the wave power, but they should play a role. The question is how important is 10% or 50%? In the ionosphere, thermosphere altitude, probably the wave, but depends on the wave scale as well. What you're talking about, like short wave or probably it's not the dominant factor. Yeah, I would say. But I'm going to say there should have some wave, and depend on the condition as well. If you're in a strong condition, probably more wave will bounce back and forth from magnetosphere and ionosphere than the quiet time. But in the quiet time, parametrically may not be the major contributor. Thank you. Actually, our current model, you kind of touch the limitation of our current model. Most GCM assume electrostatic, so we don't have the capability to even simulate the wave bouncing back and forth because the dBdt is equal 0. But it's very interesting. I think in the future, maybe we should try to release that assumption, see how significant it will be. I remember Paul Song, he did some 1D simulation to track the influence of that wave. Yeah.
Can I ask another silly question?
So
I work with the Meso-scale. So we were working with, say, t is like 0.01 second. So I know the GCMs drive dt at like 60 seconds, like high GCM 2 minutes. What if we just run high GCM at like 0.1 second and then change the electrical times? Would that give you the same answer as changing the angular variation?
Actually, I think for Gita and the TID7 has different answer. Yeah, we can talk about that. But actually, the Gita time step is 2 seconds. And even, we have sub-second, can close to 1 second. And TID7, the order of time step is minutes, per 2-3 minutes. And we have different reasons why we set up that time step. Well, maybe we can talk more details. Yeah, if we increase the time step, the some limitation may not allow you to do that, and you may get something, but may not as exactly as what you want. Yeah.
I'm just curious.
Perhaps one comment because the time step in GCM is usually much smaller than physical temporal scales that are actually described. But it may get something. So if you have a time step of 1 minute, then perhaps the scales are 30 minutes. So just tell us to shut up at some point if you're derailing.
I love question.
Talk. But I know the terms resolved scale variability and subgrid variability come up in this business here. And so the resolved scale variability, presumably you would see that in your simulation depending on the grid size and the time step. Of the variability that you're including here, is it a model for subgrid or does it include both resolved scale and subgrid? Maybe an alternative question is, what is E? Is E really just an average
You guys ask excellent questions. This electrovariability, it goes back to the way build up the how Idealization build up the model. When the build up the model, basically the recreated Weimar, and then subtract Weimar from the observation. So this variability technically represents the difference between D2 observation and the Weimar model. You can think about it, climatological average model. Since satellite should observe the most of, well, of course, precisely should be the combination of spatial variability and also could be some large scale variation as well, because Weimar can be, in large scale has some leftover. I think we should do the spatial, the spectral analysis. And my understanding is probably the major component should still represent the subgrid spatial variability. Since it's from the satellite, so the spatial variability should be dominant than the temporal variability. And the main component still should be I'm not saying all of them, but the majority is a subgrid spatial variability. Yeah. And okay, can I move on now? Thank you. Okay. And here shows a little bit more details. And the average electric field, the joule heating when we're only adding in the average electric field. Joule heating distribution when we're adding in both average E and variability E. And here is the Poynting flux. Everything's two-dimensional because we did the attitudinal integration. And after adding in the electric variability, at least the magnitude, the maximum value is closer to the Poynting flux, and distribution is we say is similar to the distribution of Poynting flux, except all the difference. Okay, If you look at it closely, you can see the polar cusp and the lattice side is still quite different. Then it brings up our future work. And this difference may be due to the inconsistence of the particle precipitation or conductance, because joule heating is proportional to both electric field and E square and conductance. If the conductance has been put not consistently with electric field convection, then you wouldn't get a reasonable joule heating distribution either. So that's why we want to develop a consistent particle precipitation model using the D2 particle data. And that's Qinyu is doing now through collaboration with Astrid and Art. Hopefully we can get some result by HU, then he can get something to present. All right. We did. Right. Okay, and the mechanism. In terms of mechanism, of course, there are many mechanisms. One of them I would like to talk about today is a non-hydrostatic process. And somebody say, okay, what is non-hydrostatic process? Why should we care about it? If you look at the vertical momentum equation for the neutral species, it has all those terms: temporal, convection, partial gradient, gravity, and friction, and Coriolis force. All those forces should balance each other. But under hydrostatic equilibrium, we just assume first, the partial gradient and the gravity force are dominant forces. All other terms are negligible compared with these two terms. Second, these two terms are balance each other all the time, everywhere. So that's the hydrostatic equilibrium. And in other words, if any term becomes comparable and important, and that case is called non-hydrostatic effect. If that's the case, actually, non-hydrostatic effects have been investigated in the no atmosphere using Earth model. If you're familiar with the no atmosphere model, Earth has two versions. One is hydrostatic version, one is no hydrostatic. If you want to study something like no resolution, large scale, the no hydrostatic version will be enough. But if you want to go to a small scale and want to study deep convection, then you have to turn on the no hydrostatic feature. in general, hydrostatic should be enough, but if you want to go to small scale and deep convection, no hydrostatic becomes important. You have to turn it on. Then the question is how it influences the upper atmosphere. It will be can we ignore them, or if it's the case, and what second condition we can ignore it. And meanwhile, the large vertical wind, like more than 100 meters per second vertical wind, has been observed ground-based and satellite. Typically, the hydrostatic model can only survive vertical wind close to 50 meters per second, and that large vertical wind. So the question, where it comes from? Does it related with non-hydrostatic process? And meanwhile, it offers the opportunity to simulate the acoustic wave. We know acoustic wave is a pressure wave. Pressure wave means the pressure needs to oscillate when the wave is propagating. But under hydrostatic equilibrium, we assume the pressure gradient is balanced by the gravity force, so it's fixed. You cannot oscillate pressure anymore. So automatically, you cannot simulate the acoustic wave. But if you release that assumption, let it go, then let the pressure to oscillate, then you have the opportunity to simulate the acoustic wave. And in 2006, my PhD advisor Aaron Ridley, myself, and Gabor Toss developed the global ionosphere thermosphere model, GITM. And GITM is very similar to TIGCM. It's a general circulation model for ionosphere, thermosphere density, velocity, and temperature. Here list some new features of GITM. Most important ones are first, it has flexible resolution. So basically, you can specify the grid point at the very beginning, in initial condition. Initially, you can specify the grid initially. So technically, the resolution can be as high as you want. And so it's a flexible parameter now. And secondly, it solves the vertical momentum equation, so it can have non-hydrostatic solution. So we can examine when the system is in the non-hydrostatic equilibrium. Here the list of the equations. If you are interested, I'm more than happy to talk to you. Actually, we always go back to the equations when we have some question to the model, we have some suspicious to the model, something's wrong. So equation is very very nice. Even it written in a very weird way, because in a numeric way, not in a physical way, if you pay attention to it. But it's okay, yeah. It is an important component of space weather modeling framework. And then we use the model, conducted several studies. First is the idealized case. We just substantially increase the geoheating in the polar region by 20 times in 2 seconds. So substantially increase the energy input in the high latitude. Then we see what's going to happen in the system. All right, here shows the temporal variation of the buoyancy acceleration at 300 kilometers. Buoyancy acceleration is defined as the difference between the pressure gradient force and the gravity force. Under hydrostatic equilibrium, this should be equal to 0 everywhere, all the time. And if you look at this plot, we'll see it's pretty much the case at the beginning, because the system has not been perturbated yet. Then during the first 3 minutes, the large upward perturbation happens, positive perturbation. Then in 5 and 7 minutes, we see a large negative perturbation followed the positive perturbation. After 10 minutes, the system goes back to the hydrostatic equilibrium pretty much, because the buoyancy acceleration is approaching to 0, right? Which indicate the non-hydrostatic effect pretty much happens during the first 10 minutes when you have variation of the energy source. Here we change the way to look at the same perturbation. The x-axis is the time, y-axis is the altitudes. Then we pick up one particular location, which is close to this point. So it's maximum perturbation location. Then we look at the temporal variation of attitudinal distribution of the buoyancy acceleration. Clearly, there is a positive disturbance propagating from low altitudes to high altitudes with increasing amplitude. Increased amplitude is understandable because the perturbation energy is conserved. Then if you go to high altitude, the density is lower, then the perturbation should be higher. And it followed by a negative phase, negative wave propagation. You can think about it like this, when you have a atomic bomb, nobody probably experienced atomic bomb in this room, right? Luckily. Well, when if you look at the movie of an atomic bomb, what's going to happen is going to first expand, then contract. This is exactly what's happening in the upper atmosphere, caused by an artificial atomic bomb. You have sudden energy input, it functions like atomic bomb, then the upper atmosphere go expand, then contract. So something like that. So we can see it goes up and it come down. If you look at the buoyancy acceleration at 400 kilometers, the magnitude is close to 2 meters per square second, which is close to 25% of the gravity acceleration. Or in another word, you can think about the pressure gradient force is 25% larger than the gravity force at this location and that particular time, which means the system is out of hydrostatic equilibrium during that period. Okay. And then we look at the phase speed and the direction and the frequency, and found that this is highly likely to be a acoustic wave. So we're very excited. We did simulate the acoustic wave in our general circulation model. And vertical wind, and such influence of artificial atomic bomb, then we see the vertical wind goes up to more than 100 meters per second easily at 400 kilometer altitudes. So we are capable to simulate large vertical wind in our model. And the vertical wind blows up the atmosphere, cause upwelling of atmosphere. The atmosphere perturbation also quite large, more than 100 can be. All right? Oh, go ahead. I'm sorry? What a setup in the...
What happens at the model top if you were to hit? So how do you extend at the model? What happens there? What kind of
our top, you're basically asking about the top boundary, the top boundary condition, or because our top boundary is an open boundary. If you have a flow with just in the ghost cell, we just assume it goes up. So, somebody say, it has drawback, of course. You kind of lost some energy in your simulation grid if you do that. Yeah, and you also will cause some artificial wave bouncing back. But since the density increase with the altitude, with altitude goes lower, so will not cause some major consequence. We just let the vertical. Well, no, we didn't give a specific number. We use the gradient. Yeah, then it continues. If we have a large vertical wind inside the domain, so in the boundary, we assume is continuous, is the same. So zero gradient. You can think about, yeah. All right, then okay. Maybe I can cut down some topic very quick. CUSP. CUSP is a very special region in the geospatial environment because the magnetic field can extend out from Earth all the way to the magnetosphere into the solar wind. And in other words, you can think about the solar wind energy and particle can get penetrated into magnetosphere and upper atmosphere. So it kind of like a special window for geospatial environment. And indeed, 2004, Hermann Neuer reported a substantial neutral density enhancement in the CUSP region is quite a bit persistent, and using the CHAMP satellite observation. The enhancement can be more than 50% compared with adjacent region, which is quite large. Such localized enhancement, and this enhancement requires more than 50% enhancement requires a lot of energy. Where the energy comes from? What's the major energy format? It's a Poynting flux or particle precipitation or the combination or something else. Or third, I think Utah State, Bob Shank's group mentioned about the possible thermal flow from top boundary of thermosphere as well. And in order to study those possible mechanisms, heating mechanisms, we set up a model and did several simulation, theoretical study. But the typical, the empirical model we used to drive GCM in high latitude does not include CASP, like Weimar or Tim-Ferrell's particle model. No, none of that. No empirical model even has CASP region. What we did is we first borrowed the climatological description of the CASP from this paper, Patrick's work, and then we put additional Poynting flux in the CASP. And the amount of Poynting flux, we use DMSP, thanks Dolores, DMSP observation, the 75 milliwatt per square meter. This is close to the probably large or maximum value of Poynting flux in the CASP, because we want to test the capability of the model to reproduce the more than 50% enhancement in the CASP. And after we add in such a substantial Poynting flux in the CASP region, the neutral density got enhanced by 35%, which is large, but not large enough compared to observation. So we need some additional energy. And then we try actually a bunch of things. First, we try the proton. But after we add in the proton, doesn't have too much. Sometimes, it depends, very slightly. Then we add in the KeV particle, like aurora particle. The consequence is just several percent at 300 kilometers, satellite trajectory. Again, not a huge difference. And next, then we try the soft electron. The 100 eV electron, even the energy flux is just 2 milliwatt per square meter, which is, more than 1 order magnitude smaller than the Poynting flux. But the consequence is, can reach 28%. So the consequence is almost comparable with the Poynting flux at a certain location. So then the question is why? It's because the total energy is so small. Why such small amount of energy can cause such huge neutral density change at 300 kilometer altitudes? This is because the soft electron can increase the electrodensity in the F region, and in the increased electrodensity in the F region can change, can enhance the conductance. When the conductance change, then the vertical distribution of Joule heating will be different. So it moves more Joule heating into up thermosphere instead of no thermosphere. And the response to that localized heating is much stronger than the heating go down to the E region, basically. So you can think about some nonlinear process could happen in the system when you put the energy in. And if you add these two together, so you can get more than 50% enhancement of neutral density in the CASP region. Wow. So that's, in terms of magnitude, is close to the observed value, more than 50%. Maybe we still miss something, could be, but at least these two can combine these two together should the major contributor. All right. We also compared the neutral wind simulation with the balloon bombed FPI observation, Hiving from Chen. And Chen's observation shows the neutral wind blows opposite to the standard TIG SAM simulation on the day side of CASP. And the model shows is poleward wind, but the observation shows equatorward wind. The question is, what makes the flip of the neutral wind on the day side of the cusp? And my previous graduate student attention did some simulation using Git model. Basically, we run the model without additional cusp energy with additional cusp energy. And then we compare the neutral wind along the balloon trajectory with having. And here, the magenta triangle shows the having observation, and the black line shows the simulation without cusp. And the blue line, light blue line, shows the simulation with cusp. Certainly, by adding in the energy in cusp, the model data comparison is much better. So now the neutral wind flipped from the poleward direction into equatorward direction on the day side region. I'm not talking about the night side. I don't know what's happening on that side. But at least on the day side, it helps a lot. Okay, but nothing's perfect. Then the next thing we did is to study the Saps. Maybe I can quickly, Saps is also typically small. It's kind of like in altitude like 1-2 degree, but it can be also much wider than that. 5 degree, more than 5 degree can happen. But typical size of Saps is below 2 degree in altitude, and we use the high resolution run, 2.5 degree in longitude and half degree in latitudes. And then we specify our run in different ways. One is the run 0, like a background run. We use the empirical model, and the run the input, we call it run 2, but actually it's run 1. Another run is we replace the forcing with the DMSP particle and convection observation along the satellite trajectory. So we got a much better specification along this satellite trajectory. And here it shows the DMSP satellite observation, and this is this 4R particle, and this panel shows the ion drift. So the black line marked the location of the aurora. Outside of the aurora, we see a large westward convection, which satisfies the definition for Saps. So we see the DMSP observed as Saps. And then we put it into, at least along the satellite trajectory region, we put it into the GATEM, and the dashed line is without Saps and the solid line with Saps. So the westward convection got enhanced dramatically. And here it shows the influence on the neutral wind. So the westward neutral wind also got enhanced due to the unneutral drag. And the northward wind got changed. Maybe, it could be both way. Either way, northward or southward, depending on location. Because when you change the ion drift, you may change a lot of things, like Coriolis force, ion drag force, and also change the pressure gradient force. So the balance of those different forces will cause different consequences for the northward wind, depending on the location. And if you look at the vertical wind got enhanced upward because the Saps can cause a lot of geoheating enhancement. So geoheating got enhanced, the vertical wind will be enhanced as well. And this perturbation in the neutral wind is propagating to the no latitude, and we call it Saps caused TADs. And the red line shows the neutral wind perturbation at 40 degree, and the green line shows the neutral wind perturbation at 20 degree. So they're propagating all the way from high latitudes to no latitude. And we're going to currently my student is coupling GATEM with RCM, and we're going to use RCM particle precipitation and convection to specify the forcing in GATEM and simulate the influence of Saps. That's an ongoing project. And acoustic, gravity acoustic wave, I think most people probably already saw that movie. The movie showed the salami. Should I show it? Okay. Can I skip that movie or? All right, it's okay. Just to show the salami influence. Japanese salami makes waves in the ocean, and well, very exciting movie. Maybe I may focus on my science. Okay, not a surprise. Salami can cause perturbation in both acoustic wave and also gravity wave. In order to simulate the small scale gravity wave and acoustic wave, we can run our Gitten model in a domain, specific domain. So typically Gitten run globally, but we also can run it regionally. And for this case, we run in a domain like 10 degree by 10 degree. And then if we put the same amount of grid in such domain, the resolution will automatically increase to 0.08 degree. So it's much higher than the global simulation. So global simulation, if we can reach 1 degree, we say, oh, that's Meso-scale, or sub-degree, or what, if we can be higher than 1 degree, that's pretty high already. But if you run it regionally, it can be more than, can reach, well, it can even higher. It depends on what you want. And then if we go in, you can see such a small domain. We have see many small variations. Here it shows this work was done by my postdoc Sisi. Shows if we add in some perturbation at the lower boundary, and this is close to the gravity wave gravity wave-like perturbation, and this is more like acoustic wave perturbation, and the consequence in the thermosphere and the ionosphere quite different. The gravity wave, maybe the maximum value is smaller than the acoustic wave in terms of neutral density perturbation. But the gravity wave perturbation is much more broader. It can happen in a much wide area. And acoustic wave happens in much localized region. Since it's so localized and it moves so fast, the consequence in the ionosphere is much smaller than the gravity wave. So gravity wave can cause much substantial perturbation than acoustic wave. All right, and then Shimon from JPL did some event study for salami, for the salami. I didn't show, but in that movie, okay, for that particular salami, and then she compared the TEC perturbation with many satellite observations, and well, in general, they're consistent. Of course, there are some phase difference and shift. It's not perfect yet, but in general, they did a good job. They also did some simulation of the TEC perturbation caused by Alaska earthquake. And you can see the magnitude of perturbation TEC is quite close to the observation, like less than 1 TEC unit. And well, like what I said, nothing's perfect. Such is our life. No surprise. Here is currently Gitten can run in 2 different modes. One is regional. That's what we have used for the salami simulation and gravity wave, small scale gravity wave simulation. And general, most of the time we run Gitten in the global mode, which is a green line. For the regional simulation, we use an open boundary. So open boundary, it causes problem after you run it for several hours. For example, here it shows the result after 6 hours simulation. You can see the large scale flow in this high resolution domain is quite a bit different from the global simulation, which is not supposed to be, because the background flow should be the same, no matter you use a high resolution or no resolution. This is caused by the unrealistic boundary condition for the regional run, because it's open boundary. And then, under support of the Muri project, we developed a local patch grid refinement method. So we run both global and the regional mode, and we use the global mode to specify the boundary condition for the regional mode. Then the regional mode got a more realistic, boundary setup. So now you can see the new background flow in the regional simulation is much better. It's very close to the global simulation. So substantially improve the background flow for the regional simulation after we do this local touch refinement. My postdoc thesis is going to use this new structure to simulate some event, the localized event, and also may apply to the solar eclipse simulation as well. All right, the last but not least, I would like to acknowledge my collaborators and the students for their hard work and the support from NSF and Air Force and the LASA as well. And here shows some group picture in the last several years. Maybe you can identify some familiar faces here. I think Qingyu and Chen and Yan Si. I would like to also mention a little bit about the new project Muri. Muri is a 5-year project supported by the Air Force, AFOSR, Air Force Office for the Scientific Research, and it's a collaboration work with UT Dallas, UCLA, CU Boulder, and University New Mexico, Johns Hopkins, APL, and MIT, Haystack, and also HAO. I think Gang and Astrid and Art are collaborating with us in this project. And the main purpose of this project is to build up next generation advances in aerosphere thermosphere coupling at multiple scales for the environmental specification and prediction. We had our kickoff meeting in December 2016. I think everybody can see more familiar face in this picture. I think Dolores, right? Astrid, and Larry, and Anthea, and Rod, Qingyu, who else? Yeah, Yan Si, Zhiping, and I think this Toshi, yeah, Toshi. Well, don't have to point to anybody. Believe it or not, I'm supposed to submit my annual report in this month, which gives me a huge amount of pressure. Time flies, and a lot of work has been. I have to say, a lot of work has been done under this support, and it's very promising. We have, we keep a close collaboration inside the group, and we approach the interesting problem through different angle, observation and simulation, and we build up new models. So it's very exciting. We got this chance to do the work we really want to do. And I also would like to acknowledge my my support, basically my access to the supercomputer in Texas. Most of simulation have been done on the supercomputer in Texas. It's basically it's Texas Advanced Computation Center. The supercomputers we have used the non-star and Stampy. Non-star only open to UT system. So except you join us, then you cannot access it. I'm sorry, but Stampy is open to the everybody nationwide, and it used to be top 10 international wide probably 5 years ago. I'm not sure, but it was very exciting at that time. Certainly, people, caught up, catch up very quickly, in terms of the technology. And they are very busy to upgrade the system this year, and it's very exciting to see what kind of new system will be at the end of this year or beginning of next year. Be very interesting, yeah. Thank you.
Thank you for a very nice and interesting presentation. So, any questions? I guess all the questions
condition of the condition of our atmosphere will be different. Let me go back to the slides. When I say something, probably one slide equals more than 100 words. Okay, here we go. So even this perturbation, the non-hydrostatic effect pretty much ends at 10 minutes. But the consequence in the vertical wind probably lasts more than 10 minutes. So while the vertical wind will be got enhanced, then reduced, but it never goes back to zero, indeed. So it may have a constant vertical wind, but smaller than, definitely larger than the background vertical wind. And the neutral density also, after 10 minutes, they still have much larger neutral density than previous status. So in terms of heat, it's I wouldn't say necessarily increase or decrease, but it may different from the quiet time. And acoustic wave itself, probably because it's maybe it's also due to the limitation of the horizontal resolution so far in this simulation. Mainly we're only able to resolve the acoustic wave to propagate upward, then go away. And gravity wave can horizontally propagate a long distance, but acoustic wave is more likely vertically propagate than disappear. And I don't know if we increase the resolution, maybe we can resolve horizontally, but mostly, yeah, it's just probably a major difference. Gravity wave can cause perturbation horizontally for a long time. So in terms of the non-hydrostatic effect, is less than 10 minutes, but the consequence maybe is more than that.
No questions? So how often do we see this like 100 millimeter per second vertical wind?
That's a good question for Qian. I would say yes. Yeah, but it depends. If not as that, well, I wouldn't say, because the difficulty is we don't have a hydrostatic version of Giton. If we do have a hydrostatic version and no hydrostatic version of Giton, then we can compare. But if we compare Giton directly to TIGCM, actually it's a little bit unfair, because there's so many other things could be different in the model. And in terms of consequence, if no hydrostatic effect can cause large vertical wind, then the vertical wind can influence the composition in general. That, well, we didn't do the comparison, but in general, I think it should influence.
Yeah, they have a lot of consequences when you are on scale to get the food of the composition.
Yeah, so everything depends on the scale you are interested. So if the scale and in terms of spatial scale and the temporal scale. So if you're interested to more like larger scale, smooth, then probably okay. But if you're interested to small scale, go to smaller scale, or go to if you're interested to some transient, like this is like a transient phenomena, maybe no hydrostatic will play important role.
Since people are so interested about non-hydrostatic events, I do have another question. So when you're solving the equation with the inertial terms in the vertical direction, do you have to do something to make sure they go back to the hydrostatic solution exactly, or just do a simplify everything? Like when we do like self-gravity in our code, we have to do very complicated balance when everything's T0, make sure these terms balance. So yeah, exactly the hydrostatic balance. Have you tested something like this?
We didn't force it. We don't force it to be hydrostatic.
So the point is that if in the equations, the grad P and G are much bigger than any other terms, so the arrows in the round off would mix into the perturbation terms. So that's why balancing these two terms are very important.
Right. If you look at those, let me see. Okay. Even like this, the input is substantial because your heat increased by 20%. Probably only happened in some superstorm. Even in that case, the difference between the pressure gradient force and the gravity force at but this probably go to next at 400 kilometer is close to 2 meters per square second, which means the pressure gradient is 25% larger than gravity. Of course, they're out of balance, but only for such short period. Okay, and then if you go more than 10 minutes, we can check it goes back to equilibrium already.
So maybe we can talk about this later. So my
Okay.
point is that if you don't do anything special in vertical direction, then you're getting something like a numerical balance instead of exactly physical balance.
Yeah.
That is my question.
Yeah, we should check that probably. Yeah, that's good point. Yeah.
When we put gravity
Right,
in
right.
our codes got very weird, states of balance.
Really?
To do something.
Yeah, maybe we can talk about more. Yeah. Well, we can work on the equations. See, if so numerical always is a concern for model. For sure. I'm not saying there are no more numerical playing role in here.
Well, I'm not saying you're doing anything.
No. Yeah, I understand what you're talking about. Yeah, that's could be a concern. That's for sure. Yeah, but we can check the equation and we can this kind of like but of course I can not exclude the numerical factors. Right. Yeah, maybe I can talk more details and we can sit down and look at your gravity why cause such perturbation or instability.
So let's thank our speaker again.
Thank you.